I woke up this morning and poured myself a cup of coffee, and in so doing, I heuristically solved a calculus problem. I estimated rates of change and poured until the cup was full, but not over full. A similar thing is true when a dog catches a ball, or when a bird controls its flight. The main difference between these solutions and those in mathematics courses is that the solution is not written down. Notice also that the bird, in nature, risks its life for food, which is something that actually nature often does. And a lot of biological forms have been precisely tuned to their environment in order to solve the various calculus problems around them that they must in order to survive. While not writing down the solution may seem like a minor point to worry about, it is in the details of what is happening and effectively communicating that we can teach cars to drive, robots to catch balls, and drones to fly and even swarm in finely controlled synchrony. You can do this type of problem by intuition, such as you controlling a video game controller or you driving a car. And that seems to hold true until things become too complicated or fast to effectively judge, like highly nonlinear and complicated systems in motion, and then our natural intuition about change breaks down, or we physically lack the information acquisition and processing power to analyze and react. For example, in a drone swarm with quadcopters, it would be very difficult for a single operator to control the whole swarm using direct control. One needs to use algorithms. For example, follow the leader, where you control one drone and then all the other drones follow that drone according to certain governing principles about how far apart of a distance they should maintain from each other and so forth. And this can be a synchrony and swarming behavior for that particular problem. The applications of calculus go well beyond modeling a single variable in motion to very complex systems of moving things all coupled together. Several examples of these types of problems in science are weather modeling, air traffic control, chemical reaction dynamics, combustion, economics, biophysics, astrophysics, aerospace, robotics, self-driving cars, etc. Nearly everywhere you look in society today, mathematical algorithms are becoming a mainstay of our modern world. And while they may not be visible everywhere to you when you look around, if you think hard enough about the items that are around you in the world today, the software and hardware systems, the technology, and how it all works, you will see that mathematics is everywhere around you. The problem when you're trying to understand the role of mathematics is that when you look for information about, say, calculus, for example, and applications, you see things like this. What is it? Space exploration? Not even close. This is a cartoon, a very simplistic idea of what's happening. Of course, it tells a story about what's happening. It can excite younger minds thinking about the problem. It can demonstrate simple principles of physics, and that's all good. But essentially, what I'd like you to think about when you see a picture like this is that it's just a cartoon, and it is hiding a lot of the complexity that you ought to see in the problem if you look at it realistically. And so how about looking more at science for what it really is? When you look at problems in the world, we're trying to get to a place now in calculus in college where we're looking at the world for what it is, and we're thinking about solving problems at the resolution that they actually need to be solved in the world today. So for example, look at the picture of the wheel on the aircraft and then the gas dynamics, turbulent gas dynamics behind that wheel. What sorts of information would we like to extract from a simulation like that? Maybe forces on the wheel during landing, maybe drag forces in the design of the carrier, maybe some temperature considerations in certain models. Are these flaps that the wheel is going to extend from going to be able to withstand the aerodynamic forces on them? We want to calculate, for example, airflow, the pressure, the temperature, all kind of maybe the friction where the wheel touches the ground, all types of different variables, and we want to know basically all there is to know about this problem when we design a wheel on an aircraft. Similarly, we want to study global circulation models and think about, well, what would it actually take in order to model the weather on an Earth scale? We want to look at the heart inside the body and think, how can we actually get a true picture of blood flow in the heart? How can we make a model of that? What exactly would be required in order to understand the real physics of the problem? What if we wanted to study forces and temperatures on a propeller blade or an impeller blade, and we wanted to figure out the loading and how the object needs to be machined in order to withstand the forces in normal operating conditions? What if we want a safety margin? How thick should things be? How should the curves be contoured? How should they be drawn in order to give the most optimal profile for like maximum force as it spins and so on? These are the types of problems that calculus can help us answer in a very realistic way, and it's not easy to answer these problems without calculus. One simply does not have very good intuition for how much temperature will build up on a propeller blade as it spins at some thousands of RPM. It's just not something that a person can really solve very easily just by looking at it and thinking about it. It requires technical analysis in order to solve, and therein computers and calculus become the essential tool. Now, looking at your course, calculus is essentially divided into two components. You have differential calculus and integral calculus, and the two are inverse operations of each other. There's a single variable and a multivariable version, and really the single variable version is just a special case of the multivariable version, and you should be seeing this in your study of the multivariable partial derivative, where essentially the partial derivative formula is exactly the same and works exactly the same way in terms of how the secant slope becomes the tangent slope in each dimension. It is the same exact concept, but now we're just extending it to a higher dimensional framework. And you're going to find that's true also for the integral calculus, that it is also a very natural extension of the single variable case. And so our idea of where to go with this is that we want to take that framework that we've built in single variable and see how it extends to multivariable, and then from there we actually want to apply it to science. And this is one of the crucial points about what you're learning right now. You are not far in terms of where you are right now from real world applications. Being able to use what seems like a very abstract theory that's been developed and actually apply it to the real science problems that are out there. Be able to take something in the world and say, these are the questions I have about it. How can I fit this mathematics to that problem? That is a modeling consideration that does require a certain type of expert hand in order to fit a model to a particular question, rather than trying to model something in its entirety for every single problem. But that experience will come with time, and you'll see how that comment plays out depending on where you end up doing your work. An important point that I'd really just like to put out there and just help you appreciate is that you're actually right at the precipice of being able to apply your mathematics to the real world. And it may feel like the real world is very far from where you are, but actually you're very close. And the math has just been difficult the whole way through, and it remains difficult, but honestly, the light at the end of the tunnel is right in front of you. And if you're interested in science, those problems are in your near future, and we're going to take what we've learned in multivariable calculus and we're going to couple it with a little bit of computer science, and we're going to be able to solve really interesting real world problems and get at some very important problems for our world today. And so I hope that you can see a little bit more about the types of questions that people are thinking about and how calculus can be thought of in terms of its role in the modern world.